distance. All right, so we are in lesson 4.5, and we are going to look at braking distance for a car or vehicle. Oh, looks like Joe had some connection trouble. Welcome back, Joe. And so the first thing to consider is what affects braking distance. So I was just hoping to get some thoughts from you guys about that. You can either speak them or chat them.
I put one of the things, the surface of the road.
Yeah, so road surface is a big one. What else?
Come on, other people speak up.
Natalie, come on.
Age of brakes and tires, I put.
Yeah, tires, definitely. Tire condition, type of tires.
Probably what like the weather is, if it's icy.
Yeah. Weather, like rain or ice, or just dry, right? Okay.
No, or anything. How about if you're like a little bit incapacitated?
Oh, yeah, right. Yeah. Let's see, what's the right phrase for that?
Even tired could.
Yeah. So I guess the driver's mental and physical state.
Like reaction time or whatever.
Action time. Other things I was thinking of, my car has anti-lock brakes, which work often, but not all the time. So that's definitely an effect. Some kind of braking system. Let's see, there's one big one we're missing here.
How fast you're going?
Yeah, speed, that's a huge one. Velocity or speed.
Good job, Natalie.
Okay, yeah, that's a pretty good list. So I just wanted you to write in that box, tell me some things that affect braking distance. And then just thinking about it, we're going to make a prediction on what will happen to the braking distance if you were to double the speed of the car. So like if you're going 30 miles per hour, maybe it takes 10 feet to brake. What if you're going 60 miles per hour? Will the braking distance be shorter, the same, twice as long, more than twice as long? Any thought about that?
Well, I got it right, but it did say, I put the braking distance would be more than twice as long, but it said, good job. That's a reasonable prediction, but let's investigate further.
Yeah, so there are wrong answers here, but it doesn't matter too much. So I'm going to say the braking distance would be less than twice as long, just for fun. Okay, that's a reasonable prediction. We need to investigate further. Yeah, so we don't have enough information to answer this question, but it's just something to think about, you know. If you go twice as fast, will the braking distance be twice as long or not? Will it be shorter? Will it be longer? So let's check it out. So up above here, we're giving an equation about braking distance. So I'm just going to talk about this a little bit on my slide, break it down. And there are more complicated versions of this equation. There are simpler versions of this equation. We're just going with this version of the equation. All right, so important things here. So the D that we're calculating is our braking distance. So we got our D, we're trying to calculate that braking distance. And one of the really big things it depends on is the velocity of the car, the speed. So we have, notice here, we have the speed squared in the numerator here. Other things that matter, and this didn't come up in our discussion, but this is a good one, the roadway grade, remember that was at the end of the prep for this one here. So what's the pitch of the road? Is it a, you know, a relatively flat road, or is it, you know, steeper than flat, or is it just perfectly flat? So the road grade G, steepness or shallowness or flatness of the road, is important because the gravity pulls, you know, straight down toward like the center of the earth. So if you're on a pitch, that changes the way gravity kind of pulls on you. And it turns out this little g here is important. That's gravity. So we have two g's going on. We've got the road grade, the slope of the road, and then we also have our gravity here. And then as far as the tires go, or the road conditions like icy, that's all balled up into this F here, which is related to friction. So it turns out we can take the idea about what kind of tires you have, or whether it's a gravel road or a dirt road or an asphalt road, whether it's wet, dry, icy, snowy, all that gets balled up into that number F. And scientists have spent a lot of time studying things like that. And so there are these resources where you can look up, you know, if you have this kind of tire and the road is like that and it was a little bit wet, then we think this is what F would be. And F is between 0 and 1. So good tires on dry pavement, you're going to get a friction value of about 0.8 to 0.85. So that's the equation we're going to play around with here. So in any given situation, gravity is always the same, and we're going to use this number right here. In some books, you'll see that as a slightly different measurement, but this is the more standard one there, the 32.2. Sometimes I just round it to 32 for ease of calculation, but we got calculators, we can handle a 0.2 there. So what we need to know are basically how fast the car was going, what do we think the friction was based on the tires and the road conditions, and then what's the slope of the road. So that's the equation we're going to play around with right there. And then here we're asked to clean up that equation where the friction coefficient is 0.8. So that would be good tires, good road, and a very mild slope of 5%. So let's plug that in and see what we get. So for us, our F is going to be 0.8, and the slope of our road is going to be 5%, but as a decimal. So 500ths, and so we just plug it in. So D equals, we don't know the velocity yet, but we will in a minute. That's going to get squared. In the bottom, I have 2 times 32.2, parentheses, 0.8 plus 0.05. And really, we just need this whole number in the calculator as our denominator. So let's see if we agree on that denominator. Two times gravity, 32.2, times parentheses, 0.85. I get 54.74. Anybody else get that?
That's what I got.
Okay. So then my formula, I can rewrite it as D equals V squared over 54.74. So that's our equation. Now, as far as the velocity goes, this equation wants feet per second, but usually we think about miles per hour. So we're going to need a conversion if we start with miles per hour measurements. And so here's where a spreadsheet comes in handy, because if I have to do that over and over again, a spreadsheet can help me do it quicker. And if you look at the next question here, we are asked to build a table for a bunch of miles per hours. So we also have to find the feet per second. So this is where I'm going to show you how I do this on a spreadsheet for the numbers we're given. First, I might as well type my V squared divided by 54.74. Did I do that right? Looks good there. Okay. So building that table out. So again, we got to be careful here reading the fine print. The V here for the formula is feet per second. We're given miles per hour, so we have to do a conversion. We have to take those miles per hour measurements, turn them into feet per second, and then we can find our distance. So I'm just going to set up this table like it is in the problem, but in a spreadsheet. So if you want to follow along on a spreadsheet, I would recommend it.
Will it work the same on Excel as it does whatever you're going to be using?
This one will do exactly the same.
Okay, thank you.
The only big differences between Excel and Google Sheets really are when it comes to making graphs and charts. They do them a little bit different.
Okay.
Otherwise, regular calculations are pretty much the same.
All right, thank you.
Yeah. So I think it's always a good idea to give your, whatever you're working on, a title. So in Excel, you want to save it with a specific name. So let's see, I'm just going to call this breaking distance. And then usually I like to type the information I started with. So some starting information here is my G for gravity, 32.2. Now that doesn't change, so I really don't need to put it there. But what does change is the big G for the road grade. Right now that's 0.05, but the next problem might say something different. Like we might have a flatter or steeper road. And then what else do we need? Our friction. And we were given 0.8. I kind of like to type that in. And then I might as well double check my denominator here. So my denominator is equal to 2 times the 32.2 times parentheses. And on the spreadsheet, you got to do the times parentheses, otherwise it'll get confused. And then I can say, take the F number, mine's in B3, and add it to the big G number, the road grade, mine was in B2. And the cool thing about doing it that way is if for the next problem they say, oh yeah, friction, it got a little slick, the friction's now 0.6, then it automatically upgrades my denominator for me, which is kind of cool. If you need me to repeat any of those steps, let me know.
But you're recording, correct?
I am, correct.
Thank you.
All right, so then over the side, I'm going to create that table that they asked me about. So I'm given some mile per hour numbers. I need those in feet per second. And then once I get that, I can use the distance formula that we developed. And then what were we asked for miles per hour? I think it was 10, 20, 40, 80, because we were thinking about the doubling of speed. 10, 20, 40, 80. So we're going back to that earlier question. What happens to the braking distance when you double the speed? All right, so how do we change feet per second to miles per hour? Well, you could just Google it, or it goes something like this. If I start with 10 miles per hour, that really means 10 miles divided by 1 hour. And I want that to look like feet per second. So miles has to go and hours has to go. So then I multiply by conversion fractions. So since miles is in the top, I would put it in the bottom to get rid of it. And I want to change to feet. Now this means I have to know how many feet are in a mile. And I recall that it's 5,280. Does that sound right? And if we weren't sure, we could look it up.
It is.
So that allows me to get rid of miles, and I have my goal of feet, but I still have hours in the bottom. I want seconds. And we can either do hours to minutes, minutes to seconds, or just realize if 1 hour is 60 minutes and 1 minute is 60 seconds, then that's 60 times 60 or 3600 seconds in 1 hour. So I'm going to use that version right here. So then up here, to get rid of hours, hours started in the bottom. To get rid of it, I put it in the top. Seconds is going to go in the bottom, and my fraction says 1 hour is 30. My conversion equation says 1 hour is 3600 seconds. So now this tells me that if I want to get rid of hours, then I should divide by 3600. So on my calculator, I just take 10 times 5,280 divided by 3600. And so this is what we need to tell the spreadsheet to do right there. So then in my spreadsheet, I'm just going to say go next to my 10 miles per hour here, and then my feet per second column, and just take equals to start a calculation, grab the miles per hour next to me, and then multiply that by 5,280 divided by 3600, and bang, I've got feet per second. I'm going to ignore Google's autofill suggestion. So this tells me that 10 miles per hour is about 14.7 feet per second. I don't really need that many decimals. What did the problems say to do about rounding? 2 decimal places. So on your spreadsheet, somewhere there's a button for increase and decrease decimals. So if you point to them, they tell you which ones they are. I want to use the decrease. I think Excel has them switched backwards, and I just need to see 2 of them. And then I can use the magic fill button here to fill that down. Now for the distance, I'm going to use the formula we calculated, and there's 2 ways I can do that. So I'm going to show you the easy way and then the better way. So the easy way is just to go back to my notes, look at the formula I found, which is right here. And instead of typing a V, I'm just going to go grab those feet per second numbers next to me. So I could just go over here and say equals, over here, there we go, equals, and then get that velocity in feet per second, raise it to the second power with that correct key, Shift 6 on most keyboards, and then just divide by 54.74. And that's what my formula said to do. And then enter, and then click back on it, adjust it to 2 decimal places, and fill it down. That's one way to do it. It works, gets the job done, but it only works for the friction 0.8 and the road grade of 5%. If I change the road grade or the friction, it doesn't change over here because I manually typed the number 54.74. So what I'd rather do is use these numbers here so that if any of these change, it updates this column for me. Okay, but this works, right? I now have the answers I need for that question. So I'm done with that question, but is this something I could reuse later? Maybe. So here's the other way to do it. It's almost exactly the same with a slight twist. I still start off the same way. Equals, that's my speed there, square the speed, and then divide. I want this number over here that I already calculated, which is based on the numbers above. Now the problem is when I fill this formula down, it's going to change the E2 to an E3, which is good. I do want it to grab the next speed, but it's going to try and change the B4 to a B5 and then a B6. And that's a problem because that's not where the denominator lives. So when you copy formulas down, the computer wants to change the row number because that's up and down, the row number. So all I have to do is tell the computer, don't mess with the 4. Now, I went over this before in class. Does anybody remember how to tell the computer not to mess with the 4 for the B4?
Put a dollar sign in front of it.
Yeah, you throw a dollar sign in front, and that tells the computer as it reads the formula, says, whoa, okay, don't mess with row 4. And it won't mess with row 4. So, and often what happens is I forget that, and I try to run the formula anyway, and then all of a sudden I realized weird shit happens. Oh my gosh, that's not right. Why did it work here and not there? And the reason is I messed up. So I'm going to do it again. I'm going to sneak the dollar sign in to say, oh, right, that's always row 4. So I just go dollar sign 4, click back on it, now fill it down. And so again, when I double click on one of these, it says, okay, grab that speed and that denominator. If I go to the next row, it says grab this speed, same denominator. So it's changing the speed, which I want. I want it to grab the new speed each time, but I always want it to grab the same denominator. Trick is to put the dollar sign in the right spot. And it just takes some practice and experimenting. So I have the same exact numbers as before, but now if someone says, okay, well, what if we're wrong about friction? What if friction was really 0.75? Then all these numbers get updated for me automatically. Notice they're a little different than they were before. If I put the 0.8 back in, it updates them again. And that's the real power of spreadsheets that I'm hoping you guys are going to get out of this class. And it just takes practice. So we've got the answers. We just need to drop them in the right spots here and so on. So I'll give you guys a minute to do that and try and answer the next questions. All right, so we have our feet and our distances. We want to consider the next question, which was based on the initial problem. What affects braking distance? And if you double your speed, does that double the distance or something else? So we're asked to look at the speed from 10 to 20 miles per hour. So that would be the first couple rows of our table here. And then we want to complete the two statements below. The braking distance at 20 miles per hour is blank feet longer than at 10. So they're just saying, hey, subtract these two numbers, what do you get? So I'm just going to make another column here called the difference. How far are they apart? And so I want to know what is 15.72 minus 3.93. And I get, no, I don't want to continue. I get it's 11.79 apart. And looks good. So then the question is, well, how many times more is that? So what would you multiply by 3.93 to get 15.7? Now, 3.93, that's about 4. 15.72 is about 16. So what times 4 gives you 16?
I mean, like 4 times 4 is 16?
Yeah, 4 times 4 is 16. Yeah, I'm looking at these two numbers, and it looks like the second distance is 4 times the first distance. And I can double check that. Instead of subtracting them, I can just divide them.
That's what I did.
Yeah, so I'm just going to do another column for divide here, where instead of subtracting the two numbers, I'm just going to divide them. What happens if I take 15.72 and divide by the 3.93? The spreadsheet says, hey, that second number is 4 times bigger. And that's what division helps us figure out. How many times bigger or smaller is one number than the other? So I'm getting a 4 here. So I just want you to repeat the same thing from 40 to 80. So how much more is it, the distance from 40 to 80? So focusing on these next two rows here. And then how many times more is the other? And if you want to check with me before you attempt to type something in there, go for it. So this is the second part of question 5. So I'll let you play for a minute first. Feel free to ask me anything if you wishes. I'm just doing a subtraction, bigger one minus smaller one, then division. Bigger one divided by smaller one. Whoa, it's 4 times again. Why is that? Interesting. So I just want a brief note about why it's 4, and to give you another example that's kind of cool. So important part about our formula here, our distance is equal to the speed squared, and then we're dividing by some number, which isn't as important, but it is important, but in a different way. So that was 54.74. So what I want to focus on here is this idea of the square for a second, and just look at a simpler equation, y equals x squared. And what happens like when we double things? So when I look at this, I can call it x to the 2nd power, or I can read it as x squared, because literally I'm talking about a square that is x by x. And then x times x gives me that area inside. So suppose I start off with a 1 by 1 square, right? So that's just 1 by 1. And then I want to double that. Well, if I double that, it's going to be 2 by 2, right? So double the length and double the width. That makes a new square. And notice that new square is 4 times bigger than the original one, right? The original one was just made up of a single square. The 2 by 2 version is made up of 4 of those individual squares, which is kind of neat. And it really doesn't matter what we started with. So suppose instead we started with a 3 by 3 square. If we double that, wouldn't you agree that we would end up with a 6 by 6 if we were to double? And when you complete that new 6 by, oops, I didn't make that top one big enough. That would be 6 right there. And if I complete that 6 by 6 square, how many times bigger is the new square? It's 4 times bigger, isn't it? And the reason is we're doubling what our x is, and then we're squaring it. To square something like this means to multiply it by itself. Oops. And if you take 2x times 2x, that's just a bunch of multiplications. You can call that 2 times x times x. You get 4 times x squared in the end. So doubling the original measurements leads to a new result that is 4 times bigger, which is kind of cool. This extends to talk about like volume. So check this out. This is a little ahead of where we are, but it is an important idea that's going to come up in the later work that we do. Volume of like a big cube would be x times x times x, x to the 3rd power. So think about a cube. I'm going to try to draw a cube to the best of my artistic ability. So here's my 2D version of a 3D cube, and it measures x wide by x long by x tall. So volume is x times x times x, or x to the 3rd power. Now, if we go and do something like double all of those x's, so let me come down here. So it was this wide. Now it's going to be that wide, right? So I'm trying to double that. I'm going to do the same thing for the length. The length was that wide. I'm going to double it. I'm going to make it that wide right there. And then the height, it was this tall right here, and I'm doubling that. So I'm making it this tall. So I'm doubling all the sides. Double. Double, it doesn't look like the cube yet, but I'm getting there. So then the front face of this, double, it's going to be right there. So here's the front face of it right there. And we can see that familiar 4 squares when we double the front face, but every face got doubled. The side face got doubled, the top face got doubled, which means in area-wise it got quadrupled. but it gets even better. And I want you to think about this for a minute. Take a look at this picture. So this is I doubled all of my x's here. How many times bigger is this new cube? How many of the old cubes do you see living in here? Is my art good enough for you guys to picture that?
What do you mean old cubes? Like,
so here's my original cube right here, right?
like, yeah.
How many of these live here?
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12.
No, just so the cube. So imagine this is like a sugar cube, like a dice
Yeah.
you could roll. So if this was
Okay.
like a dice you roll, how many dice do you see right here? I see 1, 2, 3, 4 on top, and I see 4 underneath. I think I see 8 of the original cubes.
Oh, okay, of the original. You're not counting the side.
No, those aren't, the sides are just squares, right? A cube is this 3D thing like a dice.
Okay.
Right, so if we think about that might be a dice right there. If I double the width, the height, and the length, the new version is made up of 4 of those original dice, or 8 of them, sorry, right? There's 4 on top and 4 underneath there. There's 8 of them there. So if you double the dimensions of a 3D object, the new thing is 8 times bigger. Why 8? Well, basically what I did there is I replaced the x with a 2x, and then I cubed it, right? 2x times 2x times 2x. And to clean that up, that would be 2 times 2 times 2, which is my 8, and then x times x times x, which is my x squared. The x squared is like that original dice, that original cube I started with here, this whole shape. There's now 8 of them in the new version, because 2 to the 3rd power is 8. Back here, we had doubling to the 2nd power, which means the new thing area-wise is 4 times bigger. So that's kind of a cool comparison that happens. All right, so that was a little farther, but important for later. So let's see, what did we get here? Based on the pattern from the previous calculations, what will happen to the braking distance if you were to double the speed of the car before it applies the brakes? What do we get? We get it's 4 times longer, right? The braking distance. From our calculations above. And then let's see, oh, we didn't answer this one though. What if we were to triple the speed? What would happen to the braking distance? Huh. So instead of doubling my area, what if I tripled it? 1, 2, 3 by 1, 2, 3.
9.
Yeah, if I do that, then what I end up is 9 of the original things in there, right? 3 by 3, 9 times bigger. Nice. And we could actually calculate that in our spreadsheet to see. So let's see, do I have any triples here? Let's suppose we were to compare 20 miles per hour. If I triple that, that would be 60 miles per hour. And then I just want these formulas here filled down. And then I'd want to see what happens if I take the new braking distance of triple the speed divided by the original distance where I had just 20 miles per hour. And we should see, yep, it is 9 times more. So if we triple the speed, the braking distance is 9 times more. Okay, so that's an important thing to consider when we're speeding down the road. So if we're going twice as fast as we should be, it doesn't mean it's going to take twice as long to brake. It's going to take 4 times longer to brake than it would have if we were doing like the right speed. So speed matters tremendously All right, and then they wanted us to make a graph of those numbers to the best of our ability, plot those points, talk about the shape. So I'm going to give you guys a minute to work on that on your own. Okay, so here's my graph to the best of my ability. And remember, you can, if you plot a point and you don't think it's quite right, notice my cursor changes shape. I can pick it up and move it and try to replace it. And if I wanted to make my spreadsheet do this, let me zoom out on it just for a little bit, show how I did that. So really on this graph, I only want to see the miles per hour and the distance. I really don't care about the feet per second, because the graph I was asked to do here was just miles per hour velocity versus distance. Yeah, it says miles per hour up here. So if I want to skip a column on a spreadsheet, this is kind of a cool trick. If you're, let's see, a Windows or a Chromebook user, you highlight your first set of numbers and then kind of let go of the mouse for a second, hold down Control and highlight the second group. So on a spreadsheet, Control on the second click allows you to select different things. So it's select the first group, let go, hold Control, select the second group. And one important thing is if you're using this to make a chart, if you selected 4 or 5 rows here, then you have to select 4 or 5 rows there. They have to match, otherwise the spreadsheet program gets mixed up. If you're a Mac user, I believe it's Command click for the second selection. And then once you select those, you can say, hey, insert me a chart, please. And here it gave me a column chart. I wanted points. And in a spreadsheet, that's called a scatter plot. So there's my scatter. And there I can see that these points, like I plotted, don't line up. There's a different slope between the first two and the next two and the next two. So they're curving upward here. All right, so what else can we do here? We're almost done with this part. It's not straight, right? These points do not line up. I try to put a ruler or a piece of paper to that. They ain't straight. So curving upwards. What type of graph do we think this is? Linear, exponential, quadratic? None of these.
Quadratic.
Yeah, why quadratic?
Because it's like, you know how it goes like in that weird shape.
That weird curve?
Yeah, that weird curve.
Yeah,
But
so
I
that's,
almost put none of these, but I know what exponential is, and I know it's not linear.
yeah, so
So
here's another reason why it's quadratic. And I mentioned this way in the beginning of class, but it's been a long time. So the word quadratic has the root quad, and quad means four-sided. In other words, a square.
Oh, good to know.
Yeah, so the quad means find a four-sided area, which is what a square does. So quadratic really means you squared something. So that's where it comes from. Yeah, so the main reason it's quadratic is because of the square. Sometimes it's hard to tell by just looking at the shape, but all quadratics do have the same kind of shape. And we have this half of this U shape showing up here. All right, cool. We did it, we did it. Yeah, we did it. And I think that's the end. We're done. Questions on anything we've done here?